This is the second lecture in Chapter 14 about equilibrium, and we have introduced the concept of the equilibrium constant K and what the formula is for it. And so in this lecture, we're going to concentrate on how do we actually calculate K and how do we know mathematically if we're at equilibrium or not. So as a reminder, the equilibrium expression formula is concentrations of products raised to whatever their coefficients are in the balanced equation over concentration of reactants. And so the more products that have formed at equilibrium, the larger the K value is going to be. So I do want to emphasize, though, that when you are calculating K, the concentrations that get plugged into this formula have to be the concentrations at equilibrium. And so you have got to know whether or not you're at equilibrium before you can get a good handle on the value for K. K does not change. The mathematical value, numerical value of K does not change under any circumstances unless temperature. Now that is a really important fact to remember. I would jot that down and highlight it. The only variable that changes the value of K is temperature, because there'll be a lot of questions that trick you into thinking other things can change it, but they cannot. So it is possible to have different concentrations of product versus reactants at equilibrium, but the ratio of products to reactants will always be the same. So let's look at some examples for that. Notice that here are the two reactants in this reaction. Here's the product. Notice that regardless of whether we start totally with only reactants and no product, that at equilibrium, again, the ratio of products to reactants remains the same. So look at the ratio of products to reactants in all of these cases is 50. K does not change. Again, that's assuming the temperature is constant. So we can mess with the concentration of reactants and products that we begin with, as in this case, we began with all product, and it still found its way to the same equilibrium position, the ratio of products to reactants. Now, I want you to notice that the concentrations of reactants and products are not always the same. You see how they vary? But the ratio of them are the same, okay? And that's what determines K. Reaction quotient Q. So one way to determine whether or not you're actually at equilibrium is if the equilibrium constant has already previously been measured by somebody, and so that you know what that value is. What you can do is as you run a reaction, you can go ahead and plug in concentrations along the way of products over reactants, and you can see if that ratio equals the equilibrium constant or not. If that ratio does not equal K, then you're not at equilibrium. And we call that Q. All right, so, and that stands for reaction quotient. Q, the reaction quotient, has the same formula as K, but the concentrations of products over reactants can be plugged in at any point in the reaction. It doesn't have to be at equilibrium. Q is very commonly used to first establish whether or not we're at equilibrium, and then also depending on the relative value of Q compared to K, we can speculate whether the reaction needs to shift left toward reactants or right toward products in order to reach equilibrium. So again, if Q equals K, we're at equilibrium, right? So you need to be able to interpret the relative value of Q versus K and know which direction it's going to shift. So let's look at the different possibilities. If Q is greater than K, so now remember what the expression is, okay? It's products in the numerator and reactants in the denominator. So if Q is greater than K, what is there too much of? Okay, that means too much product, right? If the value of Q, that means you have too much product or not enough reactant. It says the same thing, right? And so if you have too much product, which way is a reaction going to shift? So let's look at this reversible reaction A to B. If you have too much product, too much of B, which way will this reaction shift in order to get K equal to Q, in order to reduce Q if it's too large? We would say then if Q is larger than K, the reaction has to shift left toward reactant. That will reduce the amount of product and reduce the value of Q. On the other hand, if Q is less than K, so again, that means there's not enough product. If Q is too small, not enough product. Okay, the numerator is too small. If there's not enough product, what does a reaction have to do to reach equilibrium? It has to make more product. So it means it has to shift right to make more product. An easy little trick that somebody taught me years ago, and I just think it's really handy to help you remember how to predict the direction a reaction will shift to reach equilibrium, is if you make yourself a number line and place Q and K on the number line. So just like any number line, the smaller numbers are on the left, the larger numbers are on the right, and put Q and K on the number line where their values are. So in this case, let's say Q is 4.2 and K is 0.19. So you put them on a number line, and if in order to reach equilibrium, you start with Q wherever it is on your number line and drag it to K. And whatever direction you have to move to approach K is the direction the reaction will have to move to reach equilibrium. So you can see in this case, if Q is too large, you have to shift left to reach equilibrium. If the values were the opposite, in other words, if the value for Q was 0.19 and the value for K was 4.2, again, always start with Q, and the reaction would have to shift right to reach K. Alrighty, so here are some more examples and being able to predict. So Q is a conceptual type of issue, and I recommend strongly you practice it a number of times because you can it's kind of like a house of mirrors. You can get yourself messed up pretty easily. So here would be a typical type of QK problem. Here's the reaction we're looking at. The K value is known and is given to you. And then somebody ran an experiment and they monitored the concentrations of the reactant and product and went ahead and calculated Q for you. And remember, now what you're going to do is you're always going to compare Q to K and then decide which way the reaction needs to shift in order to reach equilibrium. So go through this and make sure that you could predict these on your own without this column being there. So here's a case where Q, compare it to K, Q is smaller, it's too small. Okay, that means not enough product. The numerator is not big enough, not enough product. If there's not enough product, which way will it shift to get more product? To the right. So whether you draw a number line, whether that method helps you or the conceptual method helps you, make sure that you can make these predictions. This is just a follow-up slide to the previous slide. It kind of walks you through each set of concentrations and figuring out which way the reaction has to shift. So just remember that any Q that is less than K, the reaction will have to shift right to reach equilibrium. Any Q that is larger than K will have to shift left to reach equilibrium. Now, the lesson we're going to learn about in this lecture is something called Le Chatelier's principle. And we have learned already that when a reaction is at equilibrium, the concentrations of reactants and products stop changing. They remain constant. even though the reaction continues. I mean, the reaction is going back and forth just at the same rate it always has, but there's no observable change in the concentration to the scientists monitoring it. However, it is possible to disturb an equilibrium. Okay, so there are several ways to do it, which we'll go over. One of the most common ways is to dump in more reactant, or product. That's going to temporarily disturb an equilibrium, and the equilibrium is going to be reestablished, and that we call that Le Chatelier's principle. The equilibrium constant, remember, does not change, so adding more concentration reactants or product does not change the value of K as long as the temperature is the same, but the reaction is going to have to shift to accommodate that change in concentration you made so it can get back to the K value, the ratio of products to reactants. So Le Chatelier's principle, textbook definition, is if an equilibrium is disturbed by changing the conditions, and we'll go over the type of conditions that can do that, equilibrium will be reestablished, okay? The reaction will attempt to counteract whatever the change is. So if more reactant was added, Le Chatelier says the reaction will respond by trying to get rid of that extra reactant. So Le Chatelier tries to undo whatever we have done to disturb equilibrium. The three ways that you can disturb an equilibrium is by changing the temperature, and the temperature will in fact change the equilibrium constant itself, as well as cause a shift to the left or right. If you have gases involved, either as a reactant or product, changing the pressure will also disrupt the equilibrium and cause a shift, or changing the concentrations of products or reactants will cause a shift. And here's this is my drum beat for you all the way throughout this chapter. The standardized tests especially try to catch you on that. I've seen several multiple choice questions that will say, if I double the concentration of the reactant, what will happen to the equilibrium constant? Nothing, okay? Nothing unless the temperature is changed. All right, so let's take each of these perturbations one at a time and see what they can do to a reaction. So, changing concentration. And pressure is kind of like changing concentration. If you have a gas and you change your pressure, you're essentially changing the concentration of that gas, or it reacts the same way. So, if you add extra reactant or product, Le Chatelier says the reaction will proceed in the direction that consumes the extra material. Remember, Le Chatelier tries to undo whatever you've done to disturb the reactant. So if we add extra reactant A, and it's at equilibrium when we do that, the equilibrium goes, geez, you just messed us up. Now we got to reestablish and get back to K. How are they going to do that? They're going to get back to equilibrium by undoing what you did. So if you increase the concentration of A, how does this reaction get rid of excess A? The only way to do that is by shifting to the right. Right? Because by shifting to the right, it's going to chew up some A. It's going to get rid of some of the extra A. All right. Now, let's look at the other way. Let's say instead of reactant, we added more D, more of one of the products, and we disrupted the equilibrium. Well, Le Chatelier says the reaction will shift to undo what we just did. Since we just increased product D, the only way to get rid of D is to shift in reverse to the left, and that will chew up some D. So basically, it shifts the opposite direction to where you perturb it. If you perturb reactants, it's going to go to products. If you perturb products, it's going to go to reactants. Now, you can perturb a reaction not only by adding extra product or reactant, you can also take away reactant or product. So that's going to have an opposite effect, all right? If I remove product, and a lot of industry does this, by the way, they remove product as it's formed. If I remove one of the products, D, that's going to disrupt the equilibrium, right? It's going to make the equilibrium, not the numerator, not have enough value, right? Products are in the numerator. So which way will the reaction shift in order to compensate for reduced concentration of D? it'll shift to the right to make more D. Remember, it tries to do the opposite of whatever was done to disturb it. Same type of thing if we remove reactant. So if I pull A out, okay, that's disrupted the equilibrium. So what does the system do? It's going to shift left to make more A to try to compensate for you taking it out. Now, this is just a cool example. Ammonia is in a lot of our cleaning agents. It's a big part of fertilizer. It's a really important industrial product. And this is the reaction that's used. It's called the Haber process in industry. And what is done to increase the yield is as ammonia is formed, as the product is formed, it's removed. There's like a little valve, and I'm going to show you if I can find it. Here it is. Yeah, so you put the reactants go in, okay? They mix together, get heated, whatever, catalyzed, and they make ammonia, which comes out here. So in industry, they'll open the valve and they'll release ammonia. So you've messed up the equilibrium. So if you remove a product, which way is the reaction going to shift in order to try to reestablish equilibrium? It's going to shift to the right to make more ammonia because you removed ammonia. It's trying to fill the void you've created. And so that's perfect for industrial chemists because the more product they remove, the more that's made. And they can really drive a reaction far towards product by just removing product. So here's another example. Here's a typical multiple choice type question. Which direction will this reaction shift if the equilibrium is disturbed by increasing the pressure of sulfur trioxide? So let's think through. Sulfur trioxide is a reactant. Okay, so if we increase the pressure of this, that means we're increasing, same thing as increasing concentration. Increasing pressure of a gas means you add more of it, right? So we increase the amount of SO3. So according to Le Chatelier, it's going to try to undo, it's going to try to get rid of that extra A. And how does it get rid of SO3? The only way is to shift right to make product because it takes some SO3 up to make product. So that would cause a shift to the right. And this is just kind of a typed in answer in case you do better reading answers than listening to them. Okie doke. So determining the effect of a volume change is a little bit more involved. So you're probably going to need a few more brain cells to follow me on this. Now, a volume change is only going to affect reactions that have a gas. Okay, it's not going to have any effect if you just have liquids and solids, aqueous stuff. And if you have a volume change, it's going to require 2 steps. You're first going to have to ask yourself, what is the pressure change that is going to result in the volume change? Okay, and then think of pressure as concentration. You'll be able to figure it out, but it's kind of a 2-step. You got to convert the effect to pressure and then make your decision. So let me remind you what happens. So let's say that we're starting here. We're starting at this volume. And let's say that we increase the volume. So we go to the left here. If you increase the volume, what happens to pressure? They're inversely related. So when you increase volume, pressure decreases, right? Because the gas molecules have more room. And if you remember, pressure is caused by the frequency of collision of gas molecules against a container. So if they have more room, there's going to be less frequency of collisions. Anyway, so increase in volume, decrease in pressure. If we go the other way, so if we decrease volume, again, inverse relationship, pressure is going to increase, which means think of concentration as increasing, okay, when you're trying to figure out a Le Chatelier problem. Okay, so now, after you make sure you understand the pressure-volume relationship, think of Le Chatelier in a reaction. If we increase volume, that we've gone over. That means we decrease pressure. If you decrease pressure, how is Le Chatelier going to respond? Le Chatelier tries to undo anything you've done to disturb an electron or an equilibrium. So if you decrease pressure, Le Chatelier will shift in a direction that in turn increases pressure. Remember, it tries to do the opposite of whatever you've done. So how does it increase pressure? I'm going to work this try out for you because I don't have an example, regular example. I left one out apparently. So let's look at this example. All right. Increasing the volume. So right away, as soon as I see that, I'm like, okay, that means decreased pressure. I just do that immediately before I even read the rest of the problem. All right, I've decreased pressure. Okay. Causes the reaction to proceed which way? All right, so decreased pressure means Le Chatelier wants to do what? Le Chatelier wants to do the opposite of what I did. So Le Chatelier wants to increase pressure. How does it do that? Okay. It does that by shifting to the side that has more gas molecules. What am I talking about? Go to the balanced reaction and literally count how many molecules of gas are on the reactant side and product side. So add up the coefficients. We assume there's a 1 there, right? So the product side has 3 gas molecules or moles, whatever you want to call them, and the reactant side only has 2. All right, so the side with more moles of gas, and it's got to be a gas in order to exert pressure. So leave out anything that's solid, liquid, or aqueous. Okay, so the side with the more moles is going to create more pressure. So since Le Chatelier is trying to increase pressure, it's going to shift right to the side that has more gas molecules and that will create more pressure. All right, the third variable that we're going to talk about that you can use to disrupt equilibrium or changes in temperature, and this one is the trickiest. This is a little bit more complex even than volume. All right, so first of all, a reminder that a change in temperature not only causes a shift in the equilibrium position, like left or right, it also changes the equilibrium constant K itself. And so you have 2 factors that you need to keep track of. And the way it shifts and what it does to the equilibrium constant depends on whether the reaction is exothermic or endothermic. Now I want to remind you, we're going back to thermodynamics a bit here. Exothermic means heat is released. Do you remember the thermodynamic sign or the mathematical sign we use for an exothermic process? Minus. So just keep that in mind because that'll pop up again here. If it's endothermic, okay, there's a plus sign in front of the delta H value. So I think the easiest way to work these Le Chatelier problems is that if you are dealing with an exothermic reaction, so there are 2 ways that a question can alert you that you're dealing with an exothermic reaction. The more common way would simply be to give you the enthalpy of reaction, and you have to recognize that negative sign means exothermic, right? Or occasionally, instead of giving you the enthalpy of reaction, they will simply write heat in as a product. If heat is written in as a product, that means heat's being released. In other words, it's an exothermic reaction. All right, so if you have an exothermic reaction and you increase temperature, I want you to think, for Le Chatelier purposes, you're going to think of heat as either a product or a reactant. So when heat is a product and you increase it, that's just like increasing, it's just like increasing any product. What happens when you increase a product? The reaction will shift left. Whoops, my pen is messing up on me. Will shift left, right, to get rid of the extra product, which is heat. Okay, so to cool down, to get rid of that extra heat, it's going to shift left. And that's only for an exothermic reaction. Let's look at what happens if we have an endothermic reaction. An endothermic reaction, again, there are a couple of different ways they could tell. They could either give you a delta H value that is positive, okay, in which case that's your sign it's endothermic, or they may write heat in as a reactant, which tells you it's endothermic. Now let's look what happens if we increase the temperature and the reaction's endothermic. That's like increasing the concentration of a reactant, right? And that means the reaction will shift to the right. So if it's endothermic, temperature increases, reaction will shift right. If it's exo, it'll shift left. So here's a summary, because I know that a lot of words in this concept can get confusing. So endothermic, exothermic, and if you increase temperature and it's endothermic, it's going to shift right. If it's exothermic and you increase temperature, it's going to shift left. Okay. Now, I want to go through, in addition to causing a shift, a change in temperature is the only factor, again, that will actually change the value of K, the equilibrium constant itself. And whether or not equilibrium constant will get larger or smaller, again, depends on whether or not you have an exothermic or an endothermic reaction. So let's think about that, okay? Let's think about an endothermic reaction. Heat is a reactant. We increase temperature, which causes a shift to the right because we've increased the reactant. What happens when you shift to the right? That means you make more product. What does that do to K when you make more product? Remember, K is products in the numerator over reactants. So if you're shifting and permanently making more product, what have you done to K? You've increased it, right? You've increased the numerator. So K increases with an endothermic reaction if you increase temperature. So go through each of these scenarios and make sure you understand which way the reaction will shift to reestablish equilibrium and what will happen to the K value. And finally, just real quick, we're almost done with this PowerPoint, is the effect of a catalyst. We learned about a catalyst in kinetics, that it speeds up reaction. It's important to realize a catalyst will not affect an equilibrium. Let me say that again. A catalyst does not affect equilibrium at all. And that is because a catalyst not only speeds up the forward reaction, so let's look at our generic reaction. It not only speeds up the forward reaction, it also speeds up the reverse reaction. So remember what equilibrium is. These two rates are equal, and so there's no change. Okay, no change in the equilibrium constant, no change in the position of equilibrium when you add a catalyst. It just gets there faster. Okay, it'll reach equilibrium faster. And that is it for this second lecture in equilibrium. Next comes ice tables, everybody's not favorite part of equilibrium, but a very important part. So that's it for now.